So this is the fourth and final question for our examples on vertical motion under gravity. This one's a little bit more tricky. Let's have a look. So a ball A falls vertically from rest from the top of a tower 63 meters high. So let's get this drawn. So let's draw a tower. Let's make it a little bit longer actually. So there's the tower, this will be the floor. Here's the top of our tower. Okay, so a ball falls vertically from rest on the top of the tower. So let's say here's our ball A. It's falling vertically from rest. So from rest means its initial velocity will be 0 meters per second. And the tower is 63 meters high. So we can label that here. 63 meters. Again, we won't call this S because it's just a distance at the moment. It's not a displacement from any particular point, so we'll just leave it as a distance for now. So that's the first little bit done. So it's falling vertically. At the same time as A begins to fall, another ball B is projected vertically upwards from the bottom of the tower with speed 21 meters per second. So at the same time, we've got our ball B here, and that's being projected upwards at 21 meters per second. Now that's a little bit of a funny one because we've got two different particles acting differently. One's going up, one's going down. They've got different values for their velocities. But we'll take the positive direction as down again. So both of these balls, A and B, will both be experiencing an acceleration of 9.8 meters per second squared. But we'll treat that as going down. So A is experiencing 9.8 because that's going down, that's going with the direction. Whereas B will be experiencing minus 9.8 because it's going up, it's against the direction. But they'll both be experiencing that. And that's everything, isn't it? Vertically upwards from the bottom of the tower, speed 21. The balls collide. So at some stage, we're going to get to a point, we don't know exactly where that point is, but if we draw a little dotted line just to show that, A is going to be falling, B is going to be rising, and there's going to be a collision. They're going to hit each other. Okay. Find the distance to the point where the balls collide from the bottom of the tower. So we need to find this distance here. And we may need to use this distance here. Okay, so they're going to have traveled different distances. So let's say the displacement from the top of the tower, or this will be the displacement of A from the top, and we'll call S2, which is actually what we're trying to find as well. The value of S2 is the distance where the balls collide from the bottom of the tower, but in our working we'll use this as the displacement of B from the bottom. Okay, this one takes a little bit of time to get set up, and it's going to be a little bit tricky when we're solving it as well. And if you think about how these things are going to collide, if they both start at time 0, A is going to be falling for a certain time, B is going to be rising for a certain time. They will collide when the time is the same for both particles. Okay, so let's say the collision occurs at time capital T. So when the time reaches capital T, A will have fallen a certain distance, B will have gone up a certain distance, and that's when they'll be hitting each other. Because we've got two separate balls starting with two separate velocities, we're going to treat these differently. So let's have a look at A's motion to start with. So for A, we have U, which is 0 meters per second. It's up here. We've got A, which is 9.8 over here, because it's going downwards. So A is 9.8. We don't have the distance, but we've called it S1. And we know that the time we're looking at is the time of collision will be capital T. Okay, so we've got U, A, S, and T. So we're going to use S equals ut plus a half at squared. And then sub in. So S is S1, U is 0, so this is just 0, plus a half A 9.8, and T is capital T. And if we just sort this out, we'll get 4.9 T squared. Awkward because we've got two unknowns here. We don't know the displacement, we don't know S1, and we don't know the time, in this case T. Well, that's as good as we're going to do for that one. So let's have a look at particle B. So for B is a separate particle, so we're going to treat the kind of motion of B. We're going to treat the U as 21 meters per second, not minus 21 meters per second. So U is 21. Okay, but it's acting, that's the direction it's going in. So really the positive direction for A is that way, and the positive direction for B is this way, because that's its direction of motion. Okay, so U is 21. A this time is minus 9.8, because gravity is acting downwards, it's acting against the direction of motion of B, so it'll be minus 9.8. S is going to be the displacement, which is S2, and we know we're looking for the time when they collide, and we've called that capital T. So in a similar way, using the same formula, we can sub in, so we'll get S2 is ut, this one time it's 21 capital T, plus a half times minus 9.8 capital T squared, and then if we just tidy this up, we get 21T minus 4.9 T squared. Okay, so we've got two equations, both have got T in, but one's got S1 and one's got S2, because that distance that they're colliding, S1 and S2 could be completely different kind of values, because we don't know. It's not, if it was halfway that they were colliding, we'd know that the displacement from the top would be the same as the displacement from the bottom, but we don't know that. But what we do know is that S2, or S, we'll go for S1 in fact, with S1 will be 63 minus S2. Okay, and that's because the height of the tower is 63. So the total distance here is 63. So S1, this distance here, will be 63, the full distance, minus the value of S2. Okay, because S2 is this bit. So this bit here, S1, will be the full 63 minus S2 will give us S1. And that means we can eliminate one of our variables, and then we can solve this simultaneously. So S1 is 63 minus S2. So from this equation here, that means 63 minus S2 is 4.9 T squared. So we're going to look at this equation, which has got T and S2 in, and this equation, which also has T and S2 in. And we should be able to get our answer. So let's sub in. So 4.9 T squared equals 63 minus S2, which is 21T minus 4.9 T squared. So 4.9 T squared, 63 minus 21T plus 4.9 T squared. The 4.9 T squares will cancel on both sides, so I'll just get 21T is 63, so T is 3 seconds. So the balls collide after 3 seconds. Let's move this way. And therefore our S2, which is the distance from the bottom of the tower where they collide, remember the displacement from the bottom in our question, that's what we label S2 as. It's 21T minus 4.9 T squared, that's here, and we now know that T is 3, so we can just throw T equals 3 into there. So S2 will be 21 times by 3 minus 4.9 times 3 squared, which should be 63 minus, this is 9 times 4.9, which is 44.1. So we get 18.9 meters. And that's it. So it's a little bit more difficult. We have to form simultaneous equations here. The main thing here is we've got two different particles with different initial speeds, with gravity acting on them differently. Gravity's acting on A downwards, that's in the direction of motion, where it's acting on B downwards, but that's against the direction of motion. So we treat the two particles separately, and we can try and form these simultaneous equations. Still not quite right, because S1 and S2 are different. They're both displacements, but they are different. But then we can use the height of the tower to help us get the variable the same, and then solve simultaneously from there. And that's question 4.